Welcome. This video is going to start looking at some of the concepts gone over in section 1.3 of the Brown SL Chemistry book. So to start within 1.3, they start talking about chemical reactions and then the different types of yield, percent yield, theoretical yield, experimental or actual yield, and along with that there's also a discussion of limiting reactant. So most of this should be review. Chemical equations, by definition, are balanced, so it's really redundant to say a balanced chemical equation. If it's not balanced, it can't occur, and if it doesn't occur, it's not a chemical equation. So it represents a chemical change or rearrangement of the reactants of the atoms, the reactants atoms into new products. So the coefficients represent the ratio needed for the reaction to proceed. So it's rare that you would have one of each reactant produce exactly one of each product. Instead, more often, you have a 2 to 3 to 1 to 2 ratio or something along those lines. So that's what the coefficients are representing. And you can think of the coefficients as representing the atoms or molecules if you want to think on the individual level, or you can think of it as representing moles, which is a measurable amount, and more often how chemists think of coefficients. So moles of anything can easily be converted to mass, or mass can easily be converted to moles. And that's good because mass is what we can easily measure in the lab, but moles is how our chemical equations are represented. So for example, it says find the mass of carbon dioxide produced from the complete combustion of 100 grams of methane. Now a couple things you're going to find in IB. They do a lot of combustion reactions of what we call hydrocarbons, or specifically the alkane group. And a hydrocarbon is just what it sounds like. It's carbon and hydrogen. And the alkanes are the common ones: natural gas, propane, butane, octane or gasoline for in your car. Those are all alkanes. So you need to be able to write the combustion equation for any hydrocarbon. And it's pretty easy because it's the hydrocarbon plus oxygen, and the products are always CO2 and H2O. So first thing you need to do for this problem is write the combustion equation, then go ahead and convert your 100 grams of methane to moles, then use your molar ratio to find how much CO2 that would produce. That will be your molar amount, and then you can convert those moles to CO2. So here's my solution. My balanced equation says CH4 plus 2O2 will yield CO2 plus 2H2O. So my 100 grams of methane at 16.05 grams per mole will be 6.23 moles. I look at my equation, see it's a 1-to-1 ratio. And remember, you need to go ahead and include this ratio so that IB and myself know that you realized you had to look at the molar ratio. We aren't going to assume you looked at it unless you show us. So it's also 6.23 moles of CO2. And so I multiply by the molar mass of CO2, and I realize that 100 grams of methane will produce 274 grams of CO2, which is one of the problems with burning hydrocarbons. Then, limiting reactant and theoretical yield. A chemical equation is really a recipe showing the ingredients, the products, and their amounts. And again, typically one ingredient will run out before the others, and it will stop the reaction from continuing. So that's the limiting reactant. It limits the product made. The other reactants then will have extra, or be called the excess reactants. So then your theoretical yield is the expected or calculated quantity of product, and it has to be based on the limiting reactant. You have to know what the limiting reactant is to be able to calculate the amount of product you can expect to get, or your theoretical yield. And another word on limiting reactants: one reactant is often, that should be an is often deliberately designed to be the limiting reactant, while the other reactants are designed to be in excess, because that ensures that all the limiting reactant will be consumed, or like in the case of water purity, that you're removing all of whatever that reactant is. So like when you're trying to get lead out of water, if you add a chemical that will react with the lead, you want to add lots of that chemical to be sure that all the lead is removed from the water. Now, whatever chemical you're using, you don't want to cause harm to the water as well. If you're using an expensive reactant like silver, then you want that to be the limiting reactant, and you want your less expensive reactant to be in excess. The other thing to consider is if you have a toxic reactant that you don't want to have left over, or you don't want to have to worry about separating from the product and disposing of. So all those considerations are made when you decide which reactant you want limiting and which one excess. Okay, so an example of limiting reactant would be if you have the following balanced equation and you're told you have 18.1 grams of NH3 and you have 90.4 grams of CuO, and you're being asked to determine the mass of N2 that can form, you have to decide which one of these is your limiting reactant. And because the 2 and 3 are representing molar amounts, you can't just look at them and say, oh yeah, I've got plenty of CuO and NH3 must be my limiting reactant. You have to change these to molar amounts, and then you have to look at that 2 to 3 ratio, or the 2 to 1 ratio and the 3 to 1 ratio they have with the product we're interested in. So a couple of methods to do this. I like to convert both reactants to moles and then use the molar ratio and predict how much product each one would yield. And then the one that yields less product is obviously my limiting reactant. That's really clear for me to understand. You can also use the molar ratios of the two reactants. You can compare the molar ratio given by the equation, in this case 2 to 3, NH3 to CuO, and then you can compare the molar ratio given by the quantity you have, the 18.1 to the 90.4, but you can't compare the mass ratio of those two. You have to change those two amounts to moles, and then you can compare that molar ratio. So I'm going to work through both methods of doing this to decide which one works best for you. So my preferred method, I go ahead and take the 18.1 grams of NH3, I divide it by 17.04, which is the molar mass of NH3. I get 1.06 moles of NH3. I look at the equation and see that I'm only going to get 1 mole of N2 from 2 moles of NH3. So from my NH3, I can expect to make 0.531 moles of N2. With the CuO, 90.4 grams is a lot more, but it also has a higher molar mass. So when I divide by the 79.55, I still only get 1.14 moles of CuO. And now when I look at my molar ratio, I only get 1 mole from 3 moles of CuO, so that becomes only 0.378 moles of N2. So that means this is going to be my smaller amount of product, and CuO is my limiting reactant. Now, if we take a look at the book's method, preferred method, I believe, they compare two ratios. It's the ratios of the reactants. So it really doesn't matter if you put NH3 over CuO or vice versa. You just have to do it the same way both times. So you're going to compare the ratio that the formula gives you, which is 2 over 3, or 0.667, and then you're going to compare it with the ratio you get from the molar amounts given. So just like in the previous problem, I still have to convert the 18.1 and the 90.4 to molar amounts. There's no getting around that because that's what the equation represents as molar amounts. So I get the 1.06 and 1.114, and since I put NH3 on top in the previous ratio, then I do the same thing here, and I come up with a ratio of 0.993. Well, 0.993 is greater than 0.667, so what that's telling me is I had more NH3 in this ratio than what I needed to get the 0.667. So it's telling me NH3 is my excess, and then by default, CuO is my limiting reactant. If I'd come up with a number that was less, let's say I came up with 0.530, and I saw that that was less than 0.667, then what that's telling me is I don't have enough of the NH3 on top, or I have an excess of the CuO on the bottom, and that's why my ratio is smaller. So it's letting me know my numerator is the limiting reactant, my denominator is the excess reactant. But again, back to what we found that 0.930 is greater, the ratio is greater, so the numerator is greater than it needs to be, or an excess, and the denominator, in this case CuO, is my limiting reactant. So you're going to come up with the same answer either way. So an excess reactant is obviously the one that's not the limiting reactant, and if you have more than 2 reactants, you'll have more than one excess reactant. And you can calculate how much is left over, and often you need to because you have to separate it from the product and dispose of it. And to find out the amount of excess reactant, basically you just work backwards from when you determine the limiting reactant. You'll know how much excess reactant you actually use in the equation, and then you can convert that back to grams of excess reactant that would be left. You just subtract the amount you use from the amount you started with, and you'll have your leftover. So yields, there's percent yield, experimental yield, and theoretical yield. So far we've talked about theoretical yield, which is a calculated value based off the limiting reactant. And if you actually made that much product, you would have 100% yield, which doesn't happen. So the experimental yield is a measurement of the product you actually made. So it's also referred to as actual yield. It's the yield you get when you run the experiment, or the amount you actually get. And it's going to be less than the predicted because you're always going to have competing reactions, loss when you transfer it, like some sticking to the filter paper, impurities that are going to either inflate it or set up competing reactions, waste. There's all kinds of reasons why it'll be less than what it should be or what you predict. So then the percent yield is a comparison of the experimental and the theoretical yields. So again, it's just like any percentage. You take the part over the whole, or what you got over what you should have got, times 100%, and it should be less than 100%.